So exponential growth and decay, a lot of times we talk about, for example, like the half-life of a radioactive element, or how long it takes for some population to double in size. And those are both examples of things that grow or decay exponentially. Exponential functions have this sort of look. Y equals b to the x is kind of the standard way of writing it, and our base is positive, not equal to 1. So some examples of this would be something like y equals 2 to the x, which looks like this, or y equals 3 to the x, which essentially looks the same, except it's steeper. So instead of having the point, 0, 1, and 1, 2, you'd have the point 0, 1, and 1, 3. But every exponential function has the same sort of shape, or this shape reflected about the y-axis. If you have some base that's between 0 and 1, like 1/4 to the x, that looks like this. Thank you. So these two functions, y equals 2 to the x and y equals 3 to the x, are more examples of a function that is growing exponentially, right? As our inputs get larger, our outputs get larger. Whereas whereas 1/4 to the x is an example of a function that is demonstrating exponential decay, right? As time essentially moves forward, the output values get lesser and lesser. A couple things to be aware of. Exponential graphs all have some common themes. They all have a y-intercept, usually 0, 1 if it hasn't been shifted or modified in any way. And they all have a horizontal asymptote, which is typically y equals 0. Again, if you shift it up or down, that's going to modify things. But if it's kind of the base form where you haven't done anything like that, that's what you get. Now, what we really want to talk about is exponential growth. So typically, and there's a number of different ways of doing this, but the most, I don't want to say normal, because sometimes the other ways are abnormal, but the way I usually think about this is that when you're talking about exponential growth or decay, it is typically modeled with something like y equals c e to the k t. Now, there are lots of different ways of writing this. You might have seen it written as a equals p e to the rt if you're talking about money having interest compounded continuously. Or you might see someone write it as like, I don't know, n of t equal to and not e to the kt. And it doesn't matter what you're calling those constants. Or you might even have p equals c e to the kx. Right? These are all ways of writing the same thing. You've got some constant multiplier here. You've got your base e, which is approximately 2.7, raised to some constant times your variable. That's the whole thing every time. Doesn't matter which of these you use. Sometimes one name feels more convenient than the other because of what you're actually measuring. Like I use something like this for population because it's a P, or something like this for interest because A is for the amount of money and P is for principal. Or this is like for the number of things at time T. This is actually started with a times 0. Doesn't matter. You can call them anything you want. It's going to be fine. But let's look at this example. In bacteria culture, starts with 10 cells and doubles every 20 minutes. And what I'll point out is there's usually really only kind of like two types of questions you can ask when you're talking about exponential growth and decay. Someone can ask you, how much stuff do you have after so much time has passed? Or they can ask you, how long does it take until you have so much stuff? Yeah.
What does it say after typically?
Modeled by or modeled with. Yeah. That's I don't default you for not being able to read what I've written there because it's not the best written. That says modeled with one of these. So in this case, we're first going to ask how long until, or I should say, how many cells will there be after 3 hours? Thank you. So that's a how much stuff is there after so much time has passed? Question. 3 hours. Great. Thank you. Whenever you're dealing with exponential growth or decay, your kind of first order of business is to solve for these constants, C and K, or P and R, or whatever you're calling, right? The coefficient out here and the coefficient of your variable there. Those are always the things you want to deal with first. There might be a rare exception to that idea, but almost all the time, that's what you do first. So I'm going to use this format here. So I have n of t equals n not e to the k2. And I typically find it really easy, helpful to make a little table. A table of what time is it and how much stuff I have at that time. Or if you would prefer, think about X and Y values, inputs and outputs. So I know at time 0, how much stuff do I have? How many cells are there at time 0? Yeah, 10. And typically we need 2 data points to be able to figure this stuff out. We have 1, how much stuff we have at time 0. Do we have another data point? Could you tell me how many cells there were at some later time? Probably. Anyone want to volunteer? You do it, yeah.
This is every 20 minutes, so at 20, so x with t is a double, so maybe 20.
Right, exactly. We know that 20 minutes later we'll have double what we had. And we could make a lot of data points if we wanted to, right? You could say another 20 minutes later, it's going to double again. Another 20 minutes later, it's going to double again. We don't need any of those. We only really ever need 2 data points. Wow, that's terrible looking there. Sorry. As long as you have 2, you can figure out what your coefficient up front is and your coefficient of your variable is in the exponent. That's what we're going to do. Almost always, if you know how much stuff you have at time 0, that is your coefficient here. So if I'm thinking this is the model, I could do the work. I could say, okay, I'm going to plug in t equals 0 and n equal to 10 and get 10 on the left equals n naught times e to the k times 0. But k times 0 is 0 and e to the 0 is 1. So really, you're getting 10 equal to n naught times 1. So that n naught is equal to 10. And there's a reason it's typically or often labeled as n sub 0, because it's meaning it is the amount of stuff you have at time 0. So if you know how much you have at time 0, you can go ahead and just be like, oh yeah, I know that's going to be 10. No big deal. Sometimes they try to make it more complicated and not give you the amount you have at the very beginning, and then you do have to do a little bit more. But it's okay. And then we're going to use this other data point. We're going to plug in n equal to 20 and t equal to 20 and solve for k. So I'm going to divide both sides by 10. I'm going to get 2 equal e to the, I usually write it as 20 times k. So very standard, write the number before the letter. And then I'm going to take the natural log of both sides. So that the natural log of 2 equals the natural log of e to the 20k. But the whole point of taking the natural log of e to some stuff is you just get the stuff, right? The natural log of e to the 20k is 20k. And then we're going to divide both sides by 20. So that the natural log of 2 divided by 20 is equal to k. What does that give us? It gives us the whole model for exponential growth in this particular situation. So what we can say now is that our model, I'll write more nicely this time, is n of t equal to n naught, which we found to be 10, times e to the k, which is natural log of 2 over 20 times t. And this is how I would choose to write this. But I will point out, there are some teachers that do this a slightly different way. There is another way of writing this, which is also fairly nice, I would say. Let me show you just because I don't want to be leaving some people out. So another way of writing this, yeah, there's so many ways to get there. I'm like trying to think of the easiest way to get there. So the way I would probably get there is take this. So e to the natural log of 2 over 20 times t, I'm going to do something kind of funky. I'm going to write it as e to the t over 20 times the natural log of 2. That's not really the funky part. Then I'm going to use one of the rules of logarithms that says the natural log of x to a power is equal to that power times the natural log of x. But I'm actually going to go in the reverse direction. I'm going to say the power times the natural log of x is equal to the natural log of x to the power. And I'm going to bring this coefficient up as the power of 2. So I'm going to rewrite this as 10 times e to the natural log of 2 to the t over 20. Why would I do something crazy like that? Well, what is e to the natural log of some stuff? It's a little bit harder to answer that question. I think hopefully everyone is okay with the fact that the natural log of e to the x is just x. Or the natural log of, more generally, the natural log of e to some stuff is just the stuff. Because the base there is e. Let me ask you guys a different question. What's log base 2 of 8? Show me on your fingers. Thank you. Yeah, exactly. You're looking for the power. Power you raise 2 to get 8. So also here's another relatively not terrible question. What's log base 3 of 3 to the 1000th power? Obviously it's going to be 1000. Because you're asking the question, 3 to what power equals 3 to the 1000th power? The answer is 1000. Well, it works the other way too. Meaning, what about 2 to the log base 2 of 8? Well, we know what log base 2 of 8 is. Log base 2 of 8, well, we know it's 3. But more importantly, log base 2 of 8, if we say the words, it's the power that you raise 2 to get 8. But we're raising 2 to that power. So we get 8, because the words say it's the power that you raise 2 to. Oh, we're doing that to get 8. Oh, so we get 8. But then it also works if it's a less nice number. Like 2 to the log base 2 of 7 is 7. Because I don't know what that number is. It's something less than 3. But I know that it's the number that if you raise 2 to that power, you get 7. And we're raising 2 to that power, so we get 7. This is all a lot of words to say that e to the natural log of some stuff is just the stuff. So that we can rewrite this as n of t equal to 10 times 2 to the t over 20. This is not the way I prefer to do it generally, but it is a thing people do. If you're not doing this, you shouldn't worry about it. But so, I know sometimes some people in some classes do it this way.
Is it possible for a model to be like n parentheses t equals 10 parentheses 2 inside over t over 20?
So sorry. So that one more time. So the way we're going to say that is n of t.
N of t equals 10 times 2 to the exponent of t over 10.
I mean, yeah, that would be a
10
perfect.
over 20, sorry.
Oh,
T
let-
over 20.
I mean, I think that's the same thing that I
So
wrote.
that's, oh wait,
So yes,
yes, oh, sorry. Is the one you circled on the top,
this one here,
are you pretty much the same?
they are literally the same.
Okay.
This and this are the same thing. So you can maybe see why you might prefer to write it like this. It's a little bit nicer looking, but so many math people are so used to working with base E that a lot of times it just gets left like this because it's kind of a very standard way of doing it. But I will tell you, right, you could have started, so if you knew that things doubled every 20 minutes, you know that your base should be 2 because you're doubling, and you know the power is T over 20 because every 20 minutes needs to increase that power by 1. Let's take a look really quick just to see that this works. If I plug in T equals 0, I get n of 0 being 10 times 2 to the 0. 2 to the 0 is 1, 10 times 1 is 10. If I plug in T equals 20, 20 over 20 is 1. 2 to the 1 is 2. 10 times 2 is 20. I'm getting the exact same table values. If I plug in, let's go big, let's go 60. If I plug in 60, 60 divided by 20 is 3. 2 to the third is 8. 8 times 10 is 80. Exactly like we have up there. So it really is the same function. And some people would say it's a nicer way of writing it. I guess I would probably fall to the argument that yes, it is a nicer way of writing it. It's just not the way we're usually going to write it. Yeah.
Can I have a refresher? Why is log 2 of 83?
So one thing I want to say, when we read that, I think it's a really good idea to say the word base. So when I read log base 2 of 8, I'm always going to say the base part. And the reason why that is equal to 3 is because, well, in fact, it's a very good question, actually. It's a deep question. So let me take 1 second to finish this because there was one question I wanted to answer about this, but then actually, sure. Yeah, we'll come back to this. So why is log base 2 of 8 equal to 3? Well, to answer that question, we really need to answer the question. Wow, there's a lot of questions to answer. So I'm going to look at y equal to 2 to the x. Or preferably, for the words, preferably in function notation, f of x equals 2 to the x. The function, the inputs, we get outputs, right? And it's definitely true that f of 3 is 2 to the third, which is 8. So, inverse functions. Functions that undo what another function does. An example of this, a very nice example, is something like y equals x to the third plus 1, or I suppose f of x equals x to the third plus 1. And its inverse undoes what that does. So the inverse would be f inverse of x is x minus 1. Well, it's the cube root of x minus 1. These functions are inverses. They undo each other, meaning f of 2 is 2 cubed plus 1, which is 8 plus 1, which is 9. And f inverse of 9 should be what? Any guesses? What do we get? That's the whole deal about inverse functions. They interchange the role of the inputs and the outputs. So if a function takes an input to a specific output, the inverse function exactly undoes that and takes that output back to that same specific input. But now the roles are reversed. Right? For this function, the input is 2 and the output is 9. For this inverse function, the input is 9 and the output is 2. So, inverse functions, that's what they do. And here's the real story. We would like a function that is the inverse function of 2 to the x. So here's good old 2 to the x. We can plot some points. I can make a table even. x, 2x. And here's the typical points to plot. 0, 1, 2, 3, -1, -2, -3. And the y values are 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, 2 to the -1, which is 1/2, 2 to the -2, which is 1/4, 2 to the -3, which is 1/8. So trying to draw a not too terrible picture. We're going to get 0, 1, 1, 2, 2, 4, 3, 8 is off the chart, -1, 1/2, and so on. And it has your usual exponential shape. And now here's what we would really like. We would like, come on, pens. We would like to know what's the inverse function. Well, how do we usually find the inverse function? We switch x and y, which is totally the reason behind why the input and the output change, right? Interchange, because we are literally interchanging the roles of x and y. So if I take this function, and I interchange x and y, I now have the flip value. So instead of 0, 1, I get 1, 0. And because if y is 0, x is 1. And instead of getting 1, 2, I get 2, 1. Instead of getting 2, 4, I get 4, 2. Instead of getting 3, 8, I get 8, 3. And instead of getting -1, 1/2, I get 1/2 -1. And I get 1/4 -2. I get a vertical asymptote. So there's the inverse function. And it is a function, right? It totally passes the vertical line test. Like there's no weird, it's not, 2x is not a function that is not invertible, right? Some functions can't be inverted. Exponential functions are not those functions. They are totally invertible. And this function here is x equals 2 to the y. But here's the thing. I would really like to write that function as a function of x. I'd like to be able to solve for y. And so what we do is we invent a new function. And we call that function the log. So the reason the logarithm does what it does is because we designed it to do what it does. Right? We wanted a function that undoes what the exponential function does. And so it's exactly the log base, whatever your base is, of x. And when you see a logarithm, you should think to yourself, oh, it's just an exponent. Right? When I'm thinking about log base 2 of x or log base 2 of 8, I'm thinking, oh, that's an exponent. It's the exponent that I raised 2 to get 8. That's the whole story. I mean, it's not the whole story, but it's most of the story. So yeah, logarithmic functions come from the inverses of exponential functions. And whenever I'm looking at a logarithmic expression, I'm always asking myself, okay, I'm looking for the base raised to some power to equal the number that's in there. So if somebody wrote something like, what's log base 6 of 36? I'd be like, okay, well, 6 raised to what power equals 36? And I'd say the answer is exactly 2. It's not 6. Right? A lot of people want to say 6 times 6 equals 36. So the answer is 6. No, we're not looking for the thing you multiply by, we're looking for the thing you raise the power to, or the power you raise the base to. But I always used to be like, people would say the logarithm is an exponent, and be like, what do you? I'm like, oh yeah, it is an exponent, right? It's literally the exponent, right? So what that means, brain, do the thing. 6 raised to that power should equal 36. Because literally that power is just 2. And so when the bases here match, those functions being inverse functions undo each other. Log base 6 of 36 gets you something, and then 6 to that power undoes whatever that did and gets you back to where you started, which was 36. And yeah, it's easy to see for this example, because log base 36 of 36 we know is 2, and 6 squared we know is 36. But it is also equally true for something weird like log 7 to the log base 7 of 5. I could not tell you what log base 7 to 5 is. No person who is is not some savant mathematically. Like nobody knows what log base 7 of 5 is. That's just weird. But all of us can know that 7 raised to that power has to equal 5. No ifs, ands, or buts about it. Good question. Yeah, definitely get to the heart of what is this really about. So back to the thing we were doing, which was modeling this thing. We found the model. And I was writing the model as 10 e to the natural log of 2 over 20, I believe. Yeah, times 2. But you could also write it as 10 t to the 2 to the t over 20. Do be careful. You cannot multiply that 10 by that 2. Right? Powers happen before multiplication. So it would be very, very incorrect to say that that was equal to 20 raised to the t over 20. So it's not correct. But then the question that I was hoping to get to was that how many bacteria are there? So how many bacteria after 3 hours? Well, that's a relatively easy question to answer. It's a much easier question than actually finding the model itself. We're just going to substitute in t equal to 3. We're going to get n of 3 equals 10 times e to the natural log of 2 over 20 times 3. And without a calculator, I would just leave it like that. With a calculator, well, so here's the thing. If you're using web work, you should enter your answer like this. Or alternatively, 10 times 2 to the 3 over 20. What I'm trying to say is you do not, and it would be probably wrong to get a decimal approximation. If you pull out a calculator and say that this is approximately, do I have it written down here? I do have it. It's approximately 5,120 cells. It's probably not going to be right because it's not an exact answer.
Just I guess the simpler one.
Sure.
The top one. Would we have to convert 3 hours into minutes because the 20 represents?
Oh, you're right. I didn't account for that. We would have to do that for both of them. I was making a mistake there. So this answer is actually not correct. These are both wrong. This answer is still right because I was just looking at my notes from before. But really, I should be setting t equal to 180. So yeah, n of 180 minutes. And that's going to equal, oh, so this answer might actually be exactly correct, which is interesting. So let's take a look. So if t is, so yeah. All right, so after 180 minutes, right, that's going to be a whole amount of 20-minute intervals. Right, we're going to double the population 9 times because every 20 minutes it doubles. So we could totally, yeah, there's a couple ways you could do it. We could even just look at the chart. It'd be like t, n of t, 0, 10, 20, 20, 40, 40, 60, 80, right? It goes on. But you could totally do it this way, which feels interesting. We're almost there. Twice 1280 is 2560. And twice 2560 is 5120. So not an approximation, actually. This is a hard equality. So n of 180. Now it's hard to see it when you do it like this, right? 10 times e to the natural log of 2 over 20 times 180. The only simplification I would probably see there would be to write it as 10 times e to the 180 over 20 is 9, e to the 9 natural log of 2. On the other hand, if you write it this way, it's a little easier to see that n of 180 is 10 times 2 to the 180 over 20. 180 over 20 is 9. And 2 to the 9th is 512. So yeah, that would be the exact answer. But my other comment still stands. You should not put decimal approximations into your answer because it will usually come out as a wrong answer. my God, where's the time go? It's already 2:45. Ah. I wanted to do lots of things today, but okay, let's look at one more exponential growth and decay example, and then I wanted to still talk. Yeah, okay. Sure. So let's look at this one. A half-life of bismuth. Never heard of that. Bismuth 210 is 5 days. Exactly. How much of a 200 milligram sample will remain after 3 weeks? So 21 days. Well, we can almost guess this. We're not going to be 100%, like we can make a good estimate. After 5 days, how much is there going to be? That's a good question. So if the half-life is 5 days, that means that after 5 days, we're going to have half of what we started with. So after 5 days, if we started with 200 milligrams, how much are we going to have? And then after another 5 days, so 10 days, how much are we going to have? And then after another 5 days, so 15 days, we're going to have 5. And then after another 5 days, at day 20, we're going to have half of 25, actually, 12 and a half. And so then after 21 days, it's going to be a little bit less than 12 and a half, but not all the way down to the next half, which is 6 1/4. So we can have a good idea of what we're going to get before we actually do any of the work. But we do have to do the work to get the right answers, right? There's no, unlike the previous one, where the number of intervals of time was exactly some multiple of our original interval. This is not the case. And it's not linear. So you can't be like, oh, 1/5 of a 5 day period gets me something. It's not to work that way. So we are going to say, we know that the amount of stuff after t days is equal to the initial amount times e to the k t. And we know what the initial amount is. Oh, question. So you can do it the other way, right? So you could totally, if you wanted to, probably see that it's going to be 200 times my base would be, what is my, I don't know. See, I'm not that good at this. I'm not good at doing it this other way. There's some, yeah, 1/2 to the t over 5. I mean, that's not bad. It's totally a bias, right? I don't do it that way because that's just not the way I've ever really looked at it. So what I'm doing is I'm using the standard the typical model for exponential growth and decay, which is always constant times e to the kt. Why e? Because it's the natural base. And e is kind of, all things aside, e is kind of the best base. A lot of that's because its derivative is nicer. So when you differentiate a function like e to the x, you have nicer things happening. So that's kind of why most of the time people make this choice. But you could totally make this choice. And in fact, it's not the wrong choice to make. So is anyone doing it like this in their class? Yes, or have you even talked about exponential growth and decay? Somewhat. So you can do it either way, but I do agree. This is the longer way. And this way is probably easier. Fine. So if we do it this way, we're just going to plug in t equals 21. And we're going to get a of 21 equal to 200 times 1/2 to the 21/5, which then you would need a calculator for. It's going to be approximately, phone calculator is never what you want to use. Let's see here. I'm going to do it the sideways way. All right. Oh, come on. Where's my sideways calculator? You have to like open your phone to actually get the sideways calculator. How entertaining. So right, if we do that, we're going to have 1/2 to the 21/5. So 0.5 to the 21/5 is 4.2 is going to be easier. and then multiply that by 200, we get approximately 10.8 feet. So not terrible, right? We had a good guess, right? We said it was going to be a little bit less than 12.5. We're right on. Yeah, I guess it's biased. I'm just biased. It's not the way I like to do it. It's fine. But yeah, it totally works. If you know what percentage of stuff you have after a certain amount of time, you can totally do it this way. So another example of this would be something like, let's say we know that after, I don't know, 7 hours, 95% of the initial mass of radioactive material remains. How long until half of it remains? Or I could ask that question better. That question really should just be, what's the half-life? Because that's what that question really means. All right, so I guess I'm going to try to do it this other better way. It does feel a little better. I'm not going to lie. Like, it is easier to come up with it than to write all this other stuff out. So I know that after 7 hours, 95% of my stuff remains. So I think my equation, you guys help me out if I'm wrong here. The amount of stuff after time t. Oh, how much am I starting with? They didn't give me an initial amount. Yeah.
When we don't really, when we aren't given an initial amount, then we use natural or E.
Well, so I don't think you have to, although I would, because that's what I would do.
Not wrong. I think there would be like a problem with this like that. You said when they give you like a percentage, you can do like A over T over the initial, and that would be like a ratio.
Oh, that sounds way more complicated than what I was going to do. That sounds right. What I was going to do is I was just going to make it up. Meaning, I would say, I'm going to start with whatever I want. What's an easy number to take percentages of? 100. And then I know that I'm going to have this 0.95 to the t over 7. So let's check and make sure this is right. If my formula is right, 7 hours later, I should have 95% of what I started with. Oh, but that totally works. 7 over 7 is 1. Anything to the first power is itself. And 100 times 0.95 is 95. So I definitely ended with 95% of what I started with, which is 100. If you really wanted to, you could say the amount of time t you have is this percent. If that makes you feel good. Like, oh yeah, after 7 days, I'm left with 95%. But you don't really need to do that. All you need to think about is, if you're starting with 100, you know how to make the percents work. So then if we want to answer the question, we're trying to figure out, okay, how long until this is equal to half of what we started with? Well, what did we start with? We started with 100 because we're making good choices. So how long until this equation ends up equaling that? That's always how we find the half-life, right? We take our model and we set it equal to half of the amount that we started with. So I'm out of room here. So solving this, we're going to get, and divide both sides by 100. So I've got 0.95 to the t over 7 equal to 50 over 100, which is 1/2. That should always happen when you're finding a half-life. The thing raised to the power should equal 1/2. That doesn't happen when you're finding a half-life. You're probably making an error somewhere. And now I really don't want to use log base 0.95. Right? That is not a very typical choice. I would definitely use the natural log here, the log basing, because that is the one we usually choose to use. So I would say natural log of 0.95 to the t over 7 equals the natural log of 1/2 bring down the t over 7. That's why we took the natural log, so we get that t over 7 out of the power. And then I would say multiply both sides by 7. Divide both sides by the natural log of 0.95. I would warn you against, some people like to kind of take the shortcut and say the answer is the natural log of 1/2 divided by the natural log of 0.95 over 7. And that should be simplified, right? If you have fractions and fractions, we should simplify this. So just something to be aware of. Time is fleeting. Yeah.
So, like when we put it in this form, variable times t,
Right.
when we solve it, there's also k.
Right. Yes. So you're right. So here's the thing. This format here, you're totally right. This format here kind of negates the necessity of dealing with that constant k. But I will point out that, right, so how do I say the things I want to say? What's really happening here is this 0.95 to the t over 7. This is the same as e to the natural log of 0.95 divided by 7 times t. That would be your k value, the natural log of 0.95 over 7, if you were doing it that way. So I know it's kind of like it's kind of weird, but that's really what happens is that if you use the other model, the y equals c to the kt, you do have to work to find that k value. And then it's always ends up being something like this. But to me, and I feel like you guys probably agree, it's kind of easier just to do it this way. You should really do whatever you're more comfortable with, or whatever your teacher is making you do is what you really should do. But then if they're not making you do it anymore, do whatever you're more comfortable with. I am still more comfortable starting with, right? So the way you would get this is you would start with y equals c e to the kt. You would plug in c equal to 100. And then you would use your other data point, which is, sorry, I know I'm way up. I'm in the wrong area. There's a different problem. Right down here. If I was doing that the other way, if I did this y equals c to the kt, I would start with 100. And then the other data point is 7 hours later, I have 95% of what I started with. So when t equals 7, the amount of stuff I'm going to have is going to be 95. Because it's 95% of the 100 I started with. So then you get 95 equal to 100 e to the k times 7. And if you solve this for k, 95 over 100 is 0.95 e to the 7k. Take the natural log of both sides. And then k ends up equaling the natural log of 0.95 over 7. Just like we said it was over there. So yeah, it's maybe more work to do it this way. I don't have a better answer other than you can do it either way. I'm more used to doing it this way, so that's probably what I will default to normally, but this is also perfectly fine and also gets at the answer. Yeah, so this half-life would be this number, which then we use the calculator. I actually have a calculator on me. We use the calculator. Google is a calculator. Let's see, natural log of 0.5 divided by 7. I'm sorry, times 7 divided by natural log. Oh my gosh. So obviously I never should do this way. Brain. It's about 91-ish, 92-ish. It takes about 92 hours. Approximately. I think anyway. Oh, I know what I was doing. This, I'm not used to this trackpad on this thing, and the right side is like a weird, it's a right click. I'm used to the trackpad not being able to. So it's actually about 94.6.